American model wasn't perfect. And into this is we're going to have another astronomer, a Danish astronomer, a guy named Tycho Brahe, and he had made a number of extremely detailed and copious observations of the heavens during the 1500s, especially of the planet Mars, recording exactly when it goes up, exactly its courses. And he had books and books and books of this data. And in the course of his career, he takes on an assistant, a guy named Johannes Kepler. And when Brahe dies, Kepler is going to inherit essentially Brahe's notes. And he's going to have this giant sort of mountain of data that he's going to plow through. And what he's going to do is he's going to come up with a new model for the motion, particularly the planet Mars, based on using math. He's going to use a mathematical formula to try to come up with, okay, this is how the planets are going to move, right? Kepler's model worked. He proved mathematically that this is how things move, and he was able then to prove mathematically that the sun, heliocentric model, was the correct one. And these planetary orbits, the reason that they move the way that they do is because they are elliptical. They're not perfect circles. And moreover, they do not move at the same speed at all times. As they get closer to the sun, they speed up, and as they get further from the sun, they slow down. And his model worked. It accurately predicted the motion of the planets in the heavens. But of course, we're going to see that this ran squarely against what had been accepted Christian doctrine, that the universe was perfect and it moved in circles in perfect motion. That very much fit Christian theology, but it didn't really fit the observable phenomenon. So this is the Kepler model, right? The sun's at the center, slight elliptical orbits of the planets, and of course, this one has Pluto on it. So back in my day, we had 9 planets. So this is a little animated file giving you an idea of kind of how this motion works. As the dot gets closer to the sun, it speeds up and then it slows down. So this would actually be more closely representative of a comet rather than a planet. It's a really exaggerated ellipse, but it gives you an idea of basically how this operated. Another major figure of this is going to be Galileo Galilei. He was an Italian mathematician, and he's going to be particularly interested, at least for part of his career, in the heavens and in the moon, and he's going to construct his own telescope in order to observe the heavens. His telescope is still out there. If you want to go see it, it's in Europe, and you can, I don't know if they'll let you look through it anymore. It probably doesn't still work, but it's not as impressive as you might think with our sort of modern giant telescopes. So we've got these big observatories. It's about as powerful as probably a pair of binoculars that you can get from the store. But it was a major improvement here. And more importantly, not only was Galileo a science guy, an astronomer guy, but he was also an artist. He was a classically trained artist. And so when he looked at the moon, like when we look at the moon, we say, oh, it's got light spots and dark spots. Okay, whatever. I mean, Dalmatians have light spots and dark spots. Who cares, right? Well, when he looks at this, he doesn't just say, dark spots and light spots. He sees shadows. And shadows imply that you got a light source and a change of elevation. So instead of just light spots and dark spots, you've got craters and mountains and trenches, right, here on the moon, and it's going to be these changes of elevation. It's going to cast these shadows. This ran, though, squarely against the Catholic doctrine, which had equated the moon to the Virgin Mary. It's perfect, inviolate, and so it must be, billiard ball smooth. You can't have any changes of elevation. Well, this was not something that sat him in good stead with Catholic doctrine. He's going to also publish works describing the discoveries of moons around Jupiter, phases of the planet Venus, spots on the sun, all of which had never been observed before. So these are new discoveries. But as we're going to see, these published works challenged the Catholic idea of how science was supposed to work. And the church eventually would censure him. Now, to be fair, there's also going to be some political stuff. Apparently, Galileo was sort of friends with one pope, with one political sort of faction, and then the new pope comes in that he's not sort of, linked politically with. And so you've got a little bit of that as well. Eventually, they would put him under house arrest and make him recant his views that, of course, he knew were correct because he had proven them. But before he died, Galileo continued on with his work. He discovered the principles of inertia, constant force acceleration, so he continued working for quite some time. So there's Galileo, right? His ridiculously high forehead, really unattractive beard. But just because you're not good looking doesn't mean you can't make contributions to science, right? This is his telescope that they still have on display. I don't think it would still work anymore. This is a zoom in of the moon. A lot of us have seen this kind of thing before. today because we have modern technology. But Galileo is the first one really to be able to look at it in any kind of detail, not as good as this, and try to make sense out of this. These are spots on the sun. I don't advise you to go out and try to look at them yourself because you'll go blind and then your head will catch on fire. So you'll just have to take Galileo's word for it. One of the other experiments that Galileo apparently did was dropping things off the Leaning Tower of Pisa to prove that big objects and small objects fall at the same rate with this. Our main character, though, of all this, or the one that's going to demonstrate the biggest change, is going to be Isaac Newton. Right? He's often referred to as the symbol of Western science. And to Newton, he worked particularly on the problems of predicting motion through the universe. In order to be able to do this, though, the math hadn't quite caught up with all of the observable phenomenon that he wanted to work on, and so he had to invent his new mathematical system, and that is calculus. So for those of you taking calculus, you can thank Isaac Newton, and of course he had to invent this in order to be able to work on what he wanted to work on. He's also going to develop 3 laws of motion. Objects continue in their state until acted upon by a force. So you got something floating out there in space, it's not going to move until you push it. And then once you push it, it's going to keep going until something stops it or redirects it. The rate of the change is proportional to the force on it. Okay, cool, right? Every action has an equal and opposite reaction. Those of you who are hunters or gun aficionados can attest to that. When you pull the trigger, the bullet shoots out of one end of the firearm and the weapon recoils in the opposite direction into your shoulder. He also showed how the force of gravity works in the universe, which is sort of a big deal, right? So much so that Newtonian physics now works. It's the accepted norm until you either get really, really close to the speed of light, where it starts to break down, and it works in a different kind of way, or when you get really, really small, you're not even sure you're talking about matter anymore. That's quantum physics. So those different systems of physics, require a special frame of reference. But for our everyday world, Newtonian physics, it works. You want to shoot a capsule onto the moon, onto a specific spot, you use calculus, you use these laws of motion. Newtonian physics works perfectly. So Newton is going to utilize the work of Copernicus, Kepler, and Galileo, and he is going to then succeed in unifying their works into one finished system, and it's going to be able to explain how everything moves in the universe. So there's Newton. So Galileo is sort of unattractive kind of guy, but Newton's got he's got the flowing locks going on. He's got the nose and the lips and stuff like that. He's a good-looking dude, right? This is his greatest work, not the only one. The Principia Mathematica, right? The Principles of Mathematics. This is sort of the biggest one that he's going to produce. And supposedly, Newton, during a bout of unemployment, was visiting his sister's orchard when an apple falls out of a tree, and he wonders, why that happens, and that leads him on to his chase of how bodies move in the universe. I don't know that that's true, but why not, right? And that leads us to funny little comics, of Newton trying to get apples to fall on him with this one, right? What we're going to see, though, is as people begin to look at, well, how exactly does this work? How do I square that with my worldview? And this is going to contribute to a lot of doubt that were clouding the minds of intellectuals. A lot of people had come at this from sort of a Christian, what had been Christian science, sort of perspective, and much of the natural world seemed no longer to make sense. That they've been told, well, this is how things work because God said it was supposed to work this way, and then we're not really observing it working that way anymore, right? One of these philosophers is going to be incredibly influential. Is going to be René Descartes. He's a Frenchman, and he's going to attempt to approach this problem. And he's going to use human reason as the basis for people to be able to understand the mysteries of the universe. And he's going to give us this quote, I think, therefore I am, or in Latin, cogito ergo sum. So he's going to elevate this idea that human reason can independently investigate matter, despite the fact that, of course, it raises the philosophical problem that, of course, isn't the human mind made out of matter. And he says that human beings have dual natures. They have the body, which can be fooled, with alcohol, with drugs, with emotion, but the mind is independent. But of course, you and I both know that the mind is attached to the body, and so there are a number of sort of problems with this, but this is the idea that reason is going to be something that Descartes says, okay, reason is above everything, and it can investigate the universe in that sense. So there's Descartes. We've gotten back to sort of unattractive people. That's a bad haircut, Renee, I'm sorry, but that's just not going to get it. Now, he does have the sort of the Sean Connery mustache thing going on, but it's really not going to save him. So here's our thinker, right? I think therefore I am, I think. Right? So a little bit of surprise on that model. One of our major outproducts is the scientific method, which is something that you and I sort of subsume on a daily basis for dealing with the natural world. And part of this is going to be a product of Francis Bacon, who is one of our great sort of philosophical minds. He wasn't necessarily a great scientist. I don't know, it depends on how you want to classify science. But he urged these people that would call themselves natural philosophers at this point not to start their works with these large-scale assumptions and then try to find ways to prove them. I got this huge system of the universe, and this is how I'm going to try to prove that that's the way that it works. He says that's not the right way to go about it. He says that what we need to do is start from the particular. All right, you observe this, and then why does that happen? You use inductive reasoning, you use empirical experiments, and he also gives us the idea that the whole point of all this is for man to control nature. We're going to be in charge of nature, and this is why we do this. Okay? Now, René Descartes disagreed with this approach. He says you have to apply rational principles that can be tested with mathematical principles, and then you arrive at new conclusions, and then you sort of rinse and repeat that idea. So you get these two ideas that are sort of at each other. Newton is the one that's going to step into this debate, and he's going to fuse the two ideas together. One of empiricism, and then the other of rationality. And what you're going to come up with is the system that you and I know from like every third grade science class that we've all had, and that is the scientific method, where you start with general principles, or in this case a hypothesis, and then you test that using experimental or empirical experiments to test these theories, whether or not that in fact is the factor that's causing the observable phenomenon. So there you go, there's a scientific method, how it works, and how you do this, right? And you isolate variables, and then you experiment on them, right? So by the late 1600s, right, science was really trying pretty hard to avoid causing as much of a fluff with the church if possible. They generally didn't come out and say, well, all right, our theology is wrong because we've observed this. You'll still see some of that, but they generally didn't want to have this fight. They're just publishing, okay, this is what we saw and this is how it works, okay? Now that doesn't mean that the church is completely ignoring the work of scientists and scientific societies. Now, many of these people in the scientific movement began to come to the conclusion that reason precluded God. You can't be a reasonable person and believe in God, right? Now, another French natural philosopher, this guy Blaise Pascal, right? He argues that there's no reason that these two have to fight each other. In fact, he says that there's unity between science and religion. To him, science deals with the natural world, religion deals with the supernatural world, and there's no reason that we can't operate within both. So he says that man can be both reasonable and spiritual to this end. All right. Now, Pascal fails to completely unify science and religion. Right? This is going to be a fight that's ongoing. Right? But we're going to see that a lot of people here, especially the European part of this movement, is going to begin this slide towards secularization. That, religion, we don't think so. Okay, we're going to be moving towards science. We're going to be moving towards this kind of stuff. So, there's Pascal. There he's having a deep thought. I don't know about whatever Pascal's thinking about. Right? Now, in an era before you got instant communication, how do these ideas get disseminated to groups of people so that other people can take your ideas and begin working on their own facets? Or how do they challenge your ideas and say, well, yeah, you did this, but I think you may have done that wrong, or my conclusion is different than yours. So we're going to see that the way that you do that in an era before you can just immediately pick up a phone and call somebody is scientific societies, right? And they would form in these countries throughout, especially Europe. We would see imitations of it here in America, and to a lesser degree in the Muslim world, but it really has a different kind of character by this point in the Muslim world. And this is going to be how they're going to get this information out, and whether it's scientific thoughts and conclusions, papers, experiments, whatever. Right? Those of you that are going to get out of college and you're going to join some professional organization, it's going to be the same kind of deal, whether it's a doctor's conference or a lawyer symposium or whatever professional, some engineers conference. That's what's going to happen. They're going to go, they're going to present their data, people are going to challenge them, they're going to ask questions, and then they're going to take this and they're saying, I'm going to use it in my own career as well. Now, it shouldn't surprise us that these societies at this point in history are pretty closely tied to universities and centers of higher learning, because a lot of the people that were engaged in that kind of work also did university work as their day job. But we're also going to see that they're supported by wealthy individuals and governments. Now, the reason these two groups come in, wealthy individuals and national governments, is because of money. They see that many of the products from these scientific advances can be used either to make money or national defense, and increase national power. You invent something great like the ability to calculate the exact longitude of ships on the high seas, people can use that to make money. People can use that to know where they are for national defense, right? And so this is going to be something that they're going to want to sponsor. The most famous of these, of course, is the Royal Society in London. But this is one of these meetings of these scientific societies, right? We've got our guy on the right, and he's giving some discussion about the human body. He's got some guy up there he's pointing to. And of course, you got these other people who are asking questions, and some, yes, and then some, oh, I don't think you're right. So anyway, it's basically the same as every conference that you're going to go to in your professional career. But again, the whole reason that we are discussing all this is not for the science itself, but so that we can understand what comes next that's stimulated by this, and this is the Enlightenment.